In these problems, we're going to work on some substitution with indefinite and definite integrals. Also, we'll get to some area between the curves later on. So, area between some curves. So, first one here, we're going to evaluate the integral of cosine 3x dx. So here, what I'm looking at is this cosine 3x. I really want to write this as an integral of cosine u du, or something maybe not equal to that, but more or less that's what I'm looking for, as I see cosine of something that's relatively nice. So to approach that, what I'm going to do is I'm going to let u equal 3x, and then du, and I take a differential of both sides, I get du is 3 dx. And there's various ways you could sort of work on this, but that means that dx is 1/3 du. So just divide by the 3. And now I can take my integral, and I write this as an integral of cosine of, well, the 3x is u, but then the dx, I pick up a 1/3 du. So this is essentially what we were going for up here, but with this 1/3 popped up here. And so what we get is 1/3, the really integral of cosine u du. And let's see, the integral, it's going to be a sine u, and then I should always get my plus c here. Now, I always want to make sure I have the plus or minus sign correct here. Derivative of sine is positive cosine, so that works out. And then there's a temptation to box this up as the answer, but this has a u in it. Now, that's not quite what we want, because our problem started with x's, so we should have x's. To get the x's back, you just use the u equals 3x again. So you get 1/3 sine 3x plus c. And there's your answer. Next one. Here, very similar question, but now this is a definite integral. That is, it has bounds 0 and pi over 3. So we're going to use the same kind of strategy. This looks like sine of something. So I'm going to let my u be 4x, the thing inside of the sine. Du is 4 dx. And so then dx would be 1/4 du. And so what I'm going to get here is an integral, well, let's see, sine 4x, that's sine u, 1 dx then becomes 1/4 du. Now there's a couple of sort of schools of thought on how to approach this. One is how to approach the bounds. One is I can change my bounds now. So I can say when this is an x equals 0, so when x equals 0, u equals 4 times 0, that's 0. So my bottom bound is a u bound is a 0. When x equals pi over 3, see, then u is 4 times pi over 3. So that's 4 pi over 3. So you can change your bounds to be in terms of u. That will work out just fine. The other thing to do is just do this as do the original problem as an indefinite integral. Ignore the bounds, get an answer, and then plug the bounds into that. So some people will sort of mix the way they write that. We'll do that sort of at the end. So we get this integral sine u 1/4 du. So then this is 1/4. The antiderivative of sine u is negative cosine u. And then I evaluate from u is 0 up to u equals 4 pi over 3. So we get 1/4. When we plug in 4 pi over 3, let's see on my unit circle, pi is here, 4 pi over 3 is there. It's the smaller of the x, so it's going to be a negative 1/2, but then it's a negative, so it's a positive 1/2. Minus, plug in 0. Plug in 0, I get cosine of 0 is 1, but again, that's a plus 1. So I get 1/4 times 3/2. My answer turns out to be 3/8. Okay, what about the other method? Well, what you could have done is just said your straight up indefinite integral. Forget the 0 and pi over 3 for the time being. And say this is an integral of sine u. Use the same substitution times 1/4 du. So I'm going to use the same substitution here. Do my antiderivative. I get 1/4 times negative cosine u, really plus c. And then sub in the x. I'm going to write this as negative 1/4 cosine of 4x plus c. So I can do an indefinite integral And that means the definite integral from 0 to pi over 3, sine of 4x dx. Well, what's that? That's going to be, okay, take my antiderivative, any antiderivative, so I'm going to choose c equals 0 for simplicity. So this is then negative 1/4 cosine of 4x, going from 0 to pi over 3. I'm going to pull the negative outside. I could have done that up here. Probably would have made things a little bit simpler. Get negative 1/4, and that's going to give me cosine of, plug in pi over 3 for x. That's 4 pi over 3 minus cosine of 0. So I end up with negative 1/4. Cosine of 4 pi over 3 is negative 1/2. Cosine of 0 is 1 minus 1. So that's negative 1/4 times negative 3/2, which gives me a positive 3/8. Same answer, two different ways. Again, sort of the bookkeeping here is one method is change your bounds to go from x to u, and then you don't need to sub in for x because your bounds are now in terms of u. Or essentially do the antiderivative and then plug in sort of the values of x here. But when you do your antiderivative, you have to sort of sub back in 4x for u. These people will use both here. The other thing you'll see people do, I don't know if I have room here. Yeah, we do have room. So another thing you'll see people do, this might be more what I would do at this, probably did at this initial level, but when I think about it more now, I don't really like the way this looks. So I start off with this. I do my u-substitution here, and I say this is, let's see, sine u times 1/4 du, but then I just leave the bounds off. Sometimes I might write question marks. Often, though, actually, I would just not even write these here, you know, kind of thing. And then I say, oh, this is then 1/4 times negative cosine u, but then it goes from, you know, something to something, and then this is 1/4, and then put in the negative cosine of 4x. And actually, just to make it match what I did before, let's write it as negative 1/4 cosine of 4x. And then my x goes from 0 to pi over 3. So I go and pull these bounds out here. Essentially what I'm doing is this method in green here, is I found my antiderivative in terms of u, converted back to x. So this part, maybe here, is essentially just this part here, and then I plugged in. So essentially I did this method in green, maybe a little bit shorter, but what I don't like about this is I'm writing this equal sign here, and these two things aren't really equal because this is a definite integral, this is an indefinite integral here. I mean, I could maybe put an a and a b here and solve, but somehow that feels a bit awkward to me here, but I guess if you're used to doing that and comfortable with it, that's probably just fine. So really it's all equivalent here, it's just sort of how you want to do the bookkeeping. Next one. This one looks a little bit scarier. So it's an integral of square root of 3 plus square root of x over square root of x dx. So I look at this and I'm not real sure what to do. So I'm going to try a u-substitution. I guess that's what we're maybe supposed to be working on, so that's a good hint that that may be a good thing to do. Something to guess, I mean, you're sort of guessing and hoping something works out, is I'm going to let u be something underneath a square root. So something somewhat complicated under a square root. I'm going to choose 3 plus square root x here. So that's my u. Well, then du, so remember square root x is x to the 1/2. So the derivative is 1/2 x to the negative 1/2 dx. Those are my differentials. And I could write this as, maybe I could move the 2 to the other side and get 2 du is dx over square root of x. So the negative exponent puts that in the x to the 1/2 in the denominator. X to the 1/2 is just square root x. And now what happens here is let's just start over here. So square root 3 plus square root x all over square root x dx. Essentially, I'm going to rewrite this as square root 3 plus square root x times dx over square root x. Well, look, we've got this. If we go to u's, this is square root 3 plus square root of x is u. Dx over square root of x, hey, that works out to be 2 du. So that makes me think this was a substitution that maybe was intended or happens to actually be really useful here. And so what I get now when I do my antiderivative, I have 2. Remember, u, or square root of u, is u to the 1/2. So when I do an antiderivative, I add 1 to 1/2 is 3/2, and then I divide by that exponent is 3/2. And I guess I get my plus c. See, divide by 3/2 is multiplied by 2/3, so I get 4/3 u to the 3/2, but u is 3 plus square root x. And there I have my answer. How could you check this if you weren't sure, like you weren't really comfortable with this? Well, if you differentiate your answer, you should get the thing you started with. So let's just differentiate this. So check here. Let's maybe say this is, I don't know, call this y. And then dy dx. Okay, I have a 4/3 out in front. I take a derivative of 3 plus square root of x to the 3/2. By the chain rule, I get 3/2. 3 plus square root x to the 1/2, so it's square root. And then I have to multiply by the derivative of the inside. So I do the chain rule really twice here. Derivative of 3 plus square root of x is really just the derivative of square root of x, which is 1/2 times x to the negative 1/2. So 2 and 2 cancel with the 4. 3 and 3 cancel. And I'm left with 3 plus square root x, square root of that, 1/2. X to the negative 1/2 I can write as over square root x, and that gives me the thing I started with. So the general feeling you should get here is doing an antiderivative can be tricky. In fact, it can be sort of impossible in some technical sense, some situations. But derivatives tend to be straightforward. So these questions are sort of hard to figure out, or maybe trickier, and should be straightforward to check. Next one. So we've got definite integral from x goes from 3 to 5. We're going to do e to the 1 over x to the x squared. So another trick or sort of common thing to try is let u, I'm going to do u sub, let u be an exponent, sort of e to the 1 over x. I'm going to let u be 1 over x. I'm worried about that x squared there, but it's going to be okay, because du, well, 1 over x is x to the negative 1. So you take a derivative, you get negative x to the negative 2 dx. And note here then that's negative du is dx over x squared. So we get that x squared in the denominator here. So what we're going to get is this integral is going to be an integral of e to the 1 over x. That's just e to the u. And then dx over x squared gives me a negative du. And then my bounds, what I'm going to do is say when x is 3, u is 1/3. When x is 5, u is 1/5. Note 1/3 is actually bigger than 1/5. In some sense, that's being taken care of with this negative here. You want to keep those where they are. So the 3 goes to the bottom. You could switch those and introduce a negative. So one thing I might do here is say this is an antiderivative of e to the u du. Pull out the negative. Now, a lot of times I wouldn't do this, but you could switch your bounds to get rid of that negative, and then I have small to big. E to the u du. And then these are u bounds. Now when I do an antiderivative of e to the u, that gives me e to the u. So I get 1/5 to 1/3. And so I get e to the 1/3 minus e to the 1/5. And that is my answer. Here, except something's weird. Oh no, that's fine. So I was worried here I didn't have any x's here, but I really shouldn't have any x's because it's a definite integral, should be a number. If I did an indefinite integral, it should have x's. Note, this way, when I did this, I can't really check my answer by taking a derivative because I don't have a sort of, well, antiderivative here. I sort of plugged in the u's and I kind of short-circuited that there. But I'll go with the answer here. Next one. I'm going to do an integral of x squared over x cubed minus 4 to the 5th with respect to x. Now, what I'm going to do is I'm going to let u equal something kind of complicated here. I'm going to say x cubed minus 4. So the reason I like that then is the denominator turns into u to the 5th. What's even nicer here is du is 3x squared dx. And then I have my x squared and my dx combined, essentially to give give me the du. There's that 3, but I can deal with that pretty easily just by dividing both sides by 3 and saying 1/3 du is x squared dx. So dividing both sides of the du equals 3x squared dx equation by 3. And so now what I get for my antiderivative, the x squared and dx combine to be a 1/3 du. The 1 over x cubed minus 4 to the 5th turns into 1 over u to the 5th. So I do my antiderivative. I get my 1/3. U to the 5th is u to the negative 5th. So you add 1. Negative 5 plus 1 is negative 4. You get u to the negative 4 over negative 4 plus c. And I just plug in the x cubed minus 4. So I'll get a 1 over about negative 1 over 12. U to the negative 4 goes to the bottom as a u to the 4th. That's x cubed minus 4 to the 4th plus c. So there's my answer. I can check that again by taking its derivative and seeing if I get x squared over x cubed minus 4 to the 5th, the thing I started with. So if I let this be y, note it doesn't matter what c is to figure out dy dx because the derivative of constant is 0. So I'm going to get a negative 1/12. This is x cubed minus 4 to the negative 4. So I get a negative 4. And then I get x cubed minus 4 to the, let's see, subtract 1 is negative 5. And then multiply by the derivative of the inside is 3x squared. 3 times 4 times over 12, those all cancel. The negatives cancel out. And I am, in fact, left with x cubed over x squared over x cubed minus 4 to the 5th. So that did check out. Next one. We're going to do a definite integral this time. Integrate from 3 to 8, x minus 3 times square root x plus 1. So, again, I mean, I need to make this a little bit simpler. Sometimes I'd like to just multiply this out, but that square root messes that up. Although if that square root sort of wasn't there or was sort of nicer, it's generally easier. So I'm going to use the strategy to be u equals x plus 1. Use this thing under the square root. Just hope that works out. So du then is just dx. And so when I do my integral, see, I get, well, okay, x minus 3, that's a little bit bothersome. So I've got my x minus 3. Square root of x plus 1, that's square root of u. Dx is just du. My bounds, I could do, let's see, when x is 3, u is 4. When x is 8, u is 9. Note, if I'm doing square roots, those are perfect squares. Makes me think I'm probably on to something if this is supposed to work out relatively nicely. But I still got this x minus 3 to deal with. Well, what I can do is I can write x in terms of u. So I can take my u equals x plus 1, solve for x. That's x is u minus 1. And so x minus 3 would be u minus 4. So just subtract 3 from both sides. So what I get is a u minus 4. Now, at first glance, this doesn't look any simpler. I've still got some polynomial times a square root. But now I can distribute this square root pretty easily because it's just sort of the variable to the 1/2 power. And so what I get is a new definite integral from 9 to 4. U times square root of u is u times u to the 1/2. That's u to the 3/2 minus 4u to the 1/2 du. Then I can do my antiderivatives. U to the 3/2 gives me u to the 5/2 over 5/2 minus 4 times 1/2 plus 1 is 3/2 over 3/2. And this whole thing, I'm going to plug in u is 4, u is 9. And so what I'm going to get is I'm going to get 2/5, divide by 5/2 is multiply by 2/5, times, let's see, 9 to the 5/2. So when I do that, let's just think about how to do that off to the side. 9 to the 5/2. What I would do is think of this as 9 to the 1/2 to the 5th. That's 3 to the 5th. Okay, that's still a little bit big. 3 squared is 9, so 3 to the 4th is 81. So 3 to the 5th is going to be multiplied by 3, 243. So I get a 243. Let's see, minus 4 times plug in, 4 times 2/3. 3/2, take its reciprocal. Divide by 3/2, same thing as multiply by 2/3. and then 4 to the 3 halves. Square root of, sorry, no, it shouldn't be a 4. It should be a 9 to the 3 halves. Square root of 9 is 3. To the third is 27. So that's what I get when I plug in 9. Now I need to plug in 4. When I plug in 4, square root of 4 is 2. 2 to the 5th works out to be 32. 4 times 2/3. When I plug in 4 to u to the 3 halves, square root of 4 is 2 to the 3rd, that's 8. So I end up with, well, probably a mess here. Let's see, I'm going to get 486 over 5 minus, let's see, the 3 and the 27 cancel for a 9. 4 times 2 is 8, times 9 is 72, minus 64 over 5. And let's see, then I have 4 times 2 is 8, times 8 is 64. I'll get a plus 64 over 3. 2 negatives gives me a plus. Let's see, 486 minus 64 is 422 over 5. I'm going to write that plus 64 thirds minus 72. Let's see. Maybe I don't want to write it that way. Let's cancel the 72. Try and cancel out part of that 422 over 5. So the 72 I'm going to write as multiply top and bottom by 5. 5 times 72 is 360. I still have my plus 64 thirds. I do my subtraction and I get 62 fifths plus 64 thirds. And now I do a common denominator of 15. To multiply by 3 on the first is 186. By 5 on the second is 320 over 15. So I end up with 506 over 15. So 5. So it's 506 over 15. There should be my answer. Now, realistically, here, I'm getting lost in the arithmetic. Spending a lot of time. I might have gone here and just plugged this into my calculator. So let's see, that was 486 over 5. Minus 72. Minus 64 divided by 5. Plus 64 divided by 3. And just convert that whole thing to a fraction. Gives me 506 over 15. So I don't really think at this level the points to work on the arithmetic. Granted, it's nice to get better at those skills, you know, and so it's probably nice to work through those, but more we want to know, can you do the calculus? Next one. Here we're doing an antiderivative, or an indefinite integral, of tan squared theta times secant squared theta. So this is a trig function setup. There's various tricks here. This one, what I'm going to do is I'm going to let u equal tangent theta. And the reason that I'm thinking that is then the du, I take a really derivative of both sides. Tangent theta gives me a secant squared theta d theta. So I've got the derivative of tangent sitting right here. And so what I get here is I get an antiderivative, tangent squared theta, that's then going to be u squared, secant squared theta d theta, that's going to be du. And so then I just get u cubed over 3 plus c. So what I get, whoops, not plus, equals, and this is just then tangent cubed theta over 3 plus c. Okay, so there's that one there as well. Short and simple, but maybe intimidating. Next one, cosine natural log x over x. We're going to integrate that from 0 to 4 with respect to x. Here, I've got cosine of something kind of complicated. My hope is to let u be natural log of x and hope this sort of works out. Well, then du, if u is natural log x, would be derivative of natural log x is 1 over x dx. Well, look, we've got that x in the denominator. That will be an x in the denominator. You could write this as dx over x if you'd like. So this worked out pretty well. Cosine natural log x is cosine of u. And then dx over x, that's just du. And then my bounds, let's see, when x is 0, we get, oh, we have a problem here. So this one gets us in trouble here, because you'll notice we did these bounds. Well, when x is 0, what's natural log of 0? In some sense, that's negative infinity. when x is 4, we get natural log of 4. So I don't like this negative infinity. Really, we're doing something called an improper integral. That is sort of a limit here. It gives a little bit of trouble. So this is one where maybe I'd go back if I'm not comfortable with this and go try the indefinite integral approach. And so what I'm going to do is forget my bounds here. I'm really just going to look at doing an integral of cosine of natural log of x over x dx. That gives me this, antiderivative of cosine u du. That'll give me a sine u plus c, and that should be sine of natural log x plus c. Now, if you go and plug in here, well, let's just go and plug in with our antiderivative. So let's do a definite integral cosine natural log x over x dx. So this should be sine natural log x from 0 to 4. You can pick c to be whatever you want. Typically, we'll pick 0, although if you did a plus 3, you'd get a plus 3 with the 4, a minus 3 with the 0. You'd subtract those. They'd go away anyway. And so what I should get is sine of natural log of 4 minus, sine of natural log 0. But notice natural log 0 does not exist. So this answer really does not exist. This doesn't really work out at all here. So we have a definite integral that really didn't exist here. Next one. Okay, so we've got a square root. We're going to do an antiderivative of square root x squared plus 1 over x to the 8th. Now, this one there's a bit of a trick to. And what I'm going to do is kind of rewrite this before I sort of do the antiderivative. I'm just going to rewrite the thing inside as square root of x squared plus 1 over x squared. And I'm going to do a 1 over, or square root of times square root of 1 over x to the 6th. So basically I took this x to the 8th, split it x to the 6th and x squared, get my dx. And so what that's going to give me is a 1 over x cubed. Note this has to be x positive. We don't have a range of x. It's probably a reasonable assumption here. If x was negative, well, if x was 0, I couldn't divide by this. If x was negative, I'd get a negative 1 over x cubed. It really should be absolute value, I suppose. But I'm going to assume x is positive. You would know that from context if you're doing some kind of application problem. Maybe x is negative in your case. And then what I get is the square root. X squared plus 1 over x squared is 1 plus 1 over x squared. So all I'm doing to get that 1 plus 1 over x squared is I'm saying x squared plus 1 over x squared is x squared over, not 2, but x squared over x squared plus 1 over x squared, and then I get a 1 plus 1 over x squared. Okay, now I've got a square root of something a little bit different, but it gave me a denominator. The reason I chose the x squared is it would cancel that first term, just sort of a trick, really. And what I'm going to do now is let u equal the thing inside the square root, 1 plus 1 over x squared. Well, then du, 1 over x squared, is x to the negative 2. So this would be negative 2x to the negative 3 dx. And that's maybe, you can write it as negative 1/2 du is dx over x cubed. Well, look, that's what we have out here, dx over x cubed. And so what we end up with is square root of u times, well, not du, times negative 1/2 du. And so when I do my antiderivative, let's see, well, I get a negative 1/2 times a u to the 3/2 over 3/2. Add 1 to 1/2, and I guess plus c. And so this is, let's see, the 2's will cancel. And so I'll get a negative 1/3 times u to the 3/2, but u is 1 plus 1 over x squared to the 3/2, and then you get your plus c. So that one, a little bit tricky, a little bit of a trick to it. That's one where you probably took the first person to figure that out a little bit to sort of see what to do. And that's just a trick that you've seen before, is sort of manipulate the thing under the square root a little bit and maybe sort of factor out something here, but I sort of divided by the x squared to get the 1. Really to get an x squared in the denominator instead of the numerator. Next one. So we have an integral from -2 to 2, 4x to the 5th, x cubed plus 9. So this one, what I'm going to do, let me just say, first of all, I notice these bounds go from -2 to 2. Those are balanced around 0. So if this was an odd function that I'm integrating, the value would be 0 here. Problem is this is not. So odd would be as if you plug in a negative x. So it's odd. So maybe f is odd. That means that f of negative x is negative f of x. So like x to the 5th, that's an odd exponent, so I'd get a negative there. But the square root with the x cubed plus 9 just doesn't work that way. You get something sort of different here. So this is not odd, so I can't write down a value of 0 right away. Just, I guess, sort of unfortunate. So what we're going to do then is I'm going to do a substitution. Here, I'm going to do u is x cubed plus 9. And then du is 3x squared, derivative of x cubed, well, derivative of x cubed plus 9, so 3x squared dx. And now what I've got, though, is 4x to the 5th. So I've got a 3x squared. Let's just solve this for x squared dx. So I get 1/3 du is x squared dx. And so what I get with my integral, let's see, when x is -2, -2 cubed is -8, plus 9 is 1. 2 cubed is 8, plus 9 is 17. Now I have a 4 from here, and I have an x cubed times square root of, let's see, x cubed plus 9 is u, and then I have a really an x squared dx. Now I'm sort of mixing my x's and u's around here. I don't know, maybe I shouldn't do that. Let's just write this all in terms of x, just to be completely clear sort of what we're thinking about. So -2 to 2. And then when I integrate this, I get a, well, when I sub in, I get a 4. That -2 became the 1. +2 became a 17. Square root x cubed plus 9 is square root u. X squared dx gives me a 1/3 du. But what about this x cubed? Well, the u is x cubed plus 9, and so that means x cubed is u minus 9. So we saw this trick, or at least a similar one, a little bit earlier. So I'm going to get a u minus 9 there, and now I can distribute the square root of u sort of to the u minus 9. So let's see, 4 times 1/3, that's 4/3. Integral from 1 to 17. Square root of u times u is u to the 3/2, minus 9 square root of u, which is u to the 1/2. Do an antiderivative, I get 4/3 times u to the 5/2 over 5/2 minus 9u to the 3/2 over 3/2 from 1 to 17. And let's see, when I evaluate this, I get 4/3 times, let's see, when I do the 17, I'm going to get a 2/5. Divide by 5/2 is multiply by 2/5. Really 17 to the 5/2 minus, I'll get a 2/3, but that'll end up times 9 will end up giving me a 3/2. So 17 to the 3/2. Maybe I should do it this way, parenthesis, parenthesis, and then subtract. When I plug in the 1, I get a 2/5 minus the 3/2. Here, I don't know how you might clean this up, is I can pull out a square root of 17 here. So I'm going to get a, let's just write it this way, 4/3 times 2/5. 17 to the 5/2 is going to be 17 squared times square root of 17. So this is power 2, power half. That's 2.5 or 5/2. Minus 3/2. 17 times square root of 17. That's 17 to the 3/2. So you've got that plus 4/3 times 2/5 minus 3/2. And then when I get done, I might just kind of simplify this all. Get something times 17 with some constant. So let's just go to our calculator here. I'm going to do 4 divided by 3 times 2/5 minus 3/2. That's going to give me something negative. Whoops, let's change that to a fraction though. So that's negative 22/15 here. So that's really the 4/3. Whoops, it's 4/3 times negative of this. So I should have gotten a negative there. And so it's going to be a positive 22/15. And then I get something times square root of 17. So what I'm going to get times square root of 17 is 4/3 times, so I have 2 divided by 5 times 17 squared minus 3 divided by 2 times 17. And let's just convert that to a fraction. That's 1802 over 15. So I get plus 1802 over 15 square root of 17. I suppose you could write that as 22 plus 1802 square root of 17 over 15. Maybe you could factor out a 2 on the top if you wanted to, but probably that's good enough. Next one. Okay, now this one I'm going to use something I mentioned at the start of the last question, and that was this is actually going to be an odd function where I'm integrating from negative pi over 2 to pi over 2. So my bounds are sort of balanced here. So when I do this, what I'm going to do is f of x, let's say this is sine to the 5th of x times cosine cubed x. Well, if you looked at f of negative x, you would get sine to the 5th of negative x times cosine cubed of negative x. Well, sine has a property that it's odd. So sine of negative x is negative sine x here. And if you think about that, that means I'm really going to get negative 1 to the 5th sine to the 5th of x. Cosine is even. That is, cosine negative x just equals cosine x. I don't get the negative out in front. So the negative doesn't actually change anything on the cosine. So in the end, I get negative sine to the 5th x times cosine cubed x. Well, that's negative of f of x. So when I do a negative x, I can sort of pull the negative outside of the function. That is what it means for f to be odd. And so what that tells me is the integral from negative pi over 2 to pi over 2, or any sort of balanced interval balanced around 0, f of x dx, that equals 0. So you don't really need an antiderivative. You don't need to use the fundamental theorem of calculus. You just sort of essentially almost write down a 0 if you recognize this. Here, we'll learn later on how to deal with something like this if this wasn't balanced. It's kind of a little bit of a pain, to be honest. Maybe not so bad in that case, but that's later on. Next one. So now we're going to do some problems doing area between curves. So we're going to find the area enclosed by the curves y equals x plus 3 and y equals x squared minus 3. So first of all, let's think about a graph of this. Well, you have y equals x plus 3. Let's just graph this. How about just a quick sketch? Y equals x plus 3. So at 3, I have some kind of line like this. And x squared minus 3 is a parabola. Down at minus 3, I've got some kind of parabola. Now at some point, these are going to intersect here and here. And I'm looking for the area of this shaded region here. So that's really what I'm trying to look for. Now let's just get a nice picture here. So here's Mathematica drawing this much more nicely. Here's x squared minus 3. Here's x plus 3. You can see those graphs. And I'm looking for this shaded part in between. Now sometimes students start to wonder, well, can I have this part out here that's sort of above the line and below the parabola? Do I want that as well? Well, that would actually have an infinite area because it doesn't go all the way to the right. There's sort of an implicit assumption that we're looking for the bounded region bounded by these two. If you wanted to be more precise when you said this, you could say maybe the intersection of the regions. How about y is less than equal to x plus 3 and y is greater than equal to x squared minus 3. So that would really be the region we're looking for. Now, the reason they don't give you that is that sort of tells you which one's above the other. Something else we need is we need these bounds here. So sort of what the x values are where I have the intersections. The way to find that is you just set the y's equal to each other. So you set x plus 3 equal to x squared minus 3, and you solve this. So I can subtract x plus 3 from both sides, and I'll get x squared minus x minus 6. So I'll get 0 is x minus 3 times x plus 2. So that's going to give me x is either 3 or negative 2. So it tells me the one bound is negative 2, the other bound is 3. You can check that on the graph here. This bound is negative 2, 2 and 4, half in between is 3. Those both look very plausible. And so what this means is our area should be an integral. We're going to integrate from negative 2 to 3. I'm going to do sort of little rectangles in here, but I'm going to do the top function minus the bottom function. Here, so the length here, top minus bottom, or maybe I think of this as a line here instead of a rectangle, but I'm doing top minus bottom. Top function turns out to be the line. That's x plus 3. Bottom function, for the interval we're concerned about, is x squared minus 3. So you write down this integral. It's not going to be too hard to do. So let's just evaluate this. So I get an integral from negative 2 to 3. Let's say I give an x, then it'll be a minus x squared. 3 minus negative 3 is plus 6 dx. Now that's essentially what we had up here, but everything's negative. That makes sense here when you think about it. And then I do an antiderivative. I get x squared over 2 minus x cubed over 3 plus 6x from negative 2 to 3. And so when I evaluate that, so I plug in 3 gives me 9 halves. Let's write that more cleanly. Minus, plug in 3, I'll get 27 thirds. That's really 9. Plus 18. Minus, when you plug in negative 2. Negative 2 squared is 4 over 2. Negative 2 cubed is negative 8. So I'll get a plus 8 thirds minus 12. So we get a, let's see, 9 halves. Negative 27 thirds is minus 9. Plus 18. Minus 4 halves is 2. Minus 8 thirds, and then we get a plus 12. So let's see, I do our whole numbers. We have 18 plus 12 is 30, minus 9 is 21, minus 2 is 19. And then we have plus 9 halves and 8 thirds. Let's combine those and find a common denominator. That would be, I guess, 6. So let's see, that's 27 sixths, multiply top and bottom by 3, minus 16 sixths. So I get 19 minus 11 sixths. So I'm going to have to find a common denominator being 6. Let's see, 19 times 6. 20 times 6 is 120. 1 sixth less than that is 114. So I end up with, let's see, 103 over 6. Something that might be useful, we're doing a lot of arithmetic here. I can actually plug this definite integral into my calculator. So this calculator will go math. Toward the bottom here, there's this function integrate. This is a numerical integration. So I'm going to do x plus 3 minus x squared. I guess plus another 3 if I distribute the negative. Could use parentheses as well. I'm going to integrate x, and then I'm going to go from negative 2 to 3. I'm going to have that convert my answer to a fraction, so I hopefully get 103 over 6. And I did not. So what happened? Probably this was supposed to be a plus. 27 over 6 minus 16 over 6, that's plus, let's maybe write that here, plus 11 sixths, so it should be a plus, so that 103 should be a 125 here. So I made a little mistake with a sign. That's very typical here in these types of questions. Probably a lot of mistakes. So this is maybe important to show your work so it's clear you know essentially what's going on. And those check steps are useful as well, where I wouldn't have probably even thought to look for that hard unless I sort of plug this into my calculator to check. Next one. Find the area between the curves y equals x squared plus 4x plus 2 and y equals negative x squared minus 3x minus 1 when negative 4 is less than x less than or equal to 0. So I guess I could graph these on my calculator. So I'm going to do x squared plus 4x plus 2 and negative x squared minus 3x minus 1. And I'm going to set my window. I know my x's are supposed to go from -4 to 0. Y's, I don't know what they are. I'm just going to leave that. So let's graph. So here's the first one. There's the second one. Well, note here, the first one, so this x squared with the positive x squared, that's on top until some point, and then it's on the bottom, and then it's back on top again. So what that means here is essentially to find the area between. We're going to look for all three pieces because we got a bound on the x's. So let me show you a picture in Mathematica with that shaded. Here's the two graphs. I have an upward parabola and sort of a downward parabola. And what I'm going to look for is the areas of these three shaded pieces, but added together. So this one, because I had that x range, I could kind of truncate this here. There's certain things you could do to write that down to be more specific. Here I'm more concrete with it. But that's the way I'm going to say is implicitly what's being asked for. Now that's going to create some difficulties because my area, well, before I find my area, I need to find those intersection points. So to do that, I get x squared plus 4x plus 2 is negative x squared minus 3x minus 1. I'm going to add x squared to both sides. Gives me 2x squared. Add 3x is 7x. Add 1 is 7. Thinking about this for a bit, this looks like 2x plus 1 times x plus 3 equals 0. So I get an x, 6x. Yep, that works out. So x is going to be either -1/2 or -3. So those are my two intersection points. I might look at my graph. -3, that looks good. -1/2, that seems very plausible. So everything looks consistent. And now what I'm going to get here is my area. I'm actually going to have three different definite integrals. So I'm going to have to do a definite integral for sort of this left shaded part, a different one for the middle, and a different one for the far right. The reason I need different integrals is because the top function changes, which effectively makes my integrand sort of the negative of what it was before. So first one, I'm going to go from -4 out to -3. And in that first bit, the top function is sort of the positive x squared parabola, the upward parabola. So this is, well, let's just do, instead of writing this over and over again, let's do off to the side here, x squared plus 4x plus 2. And let's subtract negative x squared minus 3x minus 1. That's going to give me, let's see, my 2x squared plus 7x plus 3. Same thing as up here. So this one is going to be 2x squared plus 7x plus 3 dx. And then from -3 up to -1/2, I'm going to get this middle one, the sort of top, or the downward parabola is on top. So the top is the downward parabola. Well, that means I'm going to do my subtraction in the other order here. And so essentially I'm going to get a negative of 2x squared plus 7x plus 3. And then my third integral, I'm going to have to go from -1/2 up to 0, and I'm back to the 2x squared plus 7x plus 3. So I write a bunch of this down. It looks kind of bad. Going to be kind of annoying, but maybe not as bad as it looks here. So we'll do an antiderivative. My antiderivative, I'm going to get 2x cubed over 3 plus 7x squared over 2 plus 3x. And that'll go from -4 to -3. And then this negative, I'm just going to write as a minus out here. And it's the same thing. 2x cubed over 3 plus 7x squared over 2 plus 3x. And then that goes from -3 to -1/2. And then plus my antiderivative is 2x cubed over 3 plus 7x squared over 2 plus 3x from -1/2 to 0. So it gets a little bit big. Now when I plug in -3 here, so I'm going to get -3 cubed. Let's see, one of the 3's will cancel on the bottom, so that's going to give me 9, but it'll be -9, so I'll get a -18. So you plug in a -3, I'll get a 9 plus 63 halves. Plug in -3, that'll be a -9. When I plug in the -4s, I'll get a -64. 4 cubed is 64. That's -128, but I'm subtracting because it's the bottom thing I'm plugging in. So I get a +128 over 3. -4 squared is 16. 16 times 7 is, let's see, 70 plus 42, that's 112. Although, probably what's simpler to do instead of doing that, when I have 16 over 2, that's 8. 8 times 7 is 56. And I have to subtract. And I get a -12, that's a +12. And then I go over here, let's see, -1/2 cubed is -1/8. So I'll get a -1/4 times 3 is -1/12. But then I have the negative out in front, gives me a +1/12. -1/2 squared is, let's see, 1/4 times 1/2 is 1/8, so I get a 7/8. It's negative from the negative out in front. And then I'll have a -3/2 with the negative out in front, gives me a +3/2. And then I'm going to plug in my -3. So I'm going to get a -27 over 3. That's -9 times 2 is -18. But then it's +18 because it's on the bottom, but then it's -18 because of being this negative out in front. -3 squared would be 9 times 7 is 63 over 2. Negative from the bottom, but a negative out in front gives me a +63 over 2. And then I'll get a -9. I'm subtracting, makes it a positive, but the negative out in front makes it a -9. Now, note here, before we continue, you got a -18, 63/2, -9. These are the same values. And that makes sense because I plugged in the -3 and the -3. Here's the top, here's the bottom here, but then I used the negative, so it sort of changed the signs up. So that should always match up. It's a nice check here to make sure everything works out. Plug in 0. All three terms are 0. I'm just going to ignore that one, not write it down. Plug in -1/2. I'll get a -1/8 times the 2 is -1/4 times the 3 is -1/12, and I'm subtracting, so I get a +1/12. Note, again, that should match here because they're both from the -1/2. Let's say, so I get a +1/4 times 1/2 is 1/8, so I'll get a -7/8. You could just write this down +3/2. I kind of like to do this on my own just to make sure I don't make a mistake. So do it again, double check. -1/2 times x is -3/2, but then I get a +3/2. So kind of a big mess here. I get certain things doubled up. Maybe we'll write these ones or underline these ones in green here. So I get that, that, and that, that, and that. So we get the -18 doubles, so that's -36. 63/2 doubles to 63. -9 doubles to, oops, not +18. 63 to -18. So I get rid of that, that. I have a +128 over 3 minus 56 plus 12. Bang, bang, bang. 1/12 plus 1/12 will give me a 1/6. -7/8 will give me -7/4. 3/2 plus 3/2 gives me 3. And at this point, I'm going to decide that I don't really want to deal with the arithmetic. I'm going to just use my calculator. So I have a -36 plus 63. -36 plus 63. -18 plus 128 divided by 3. Minus 56 plus 12 plus 1/6 minus 7/4 plus 3. This all worked out. I get that, but I'm going to convert that to a fraction, and gives me 109 over 12. So kind of a big mess. Point is knowing that you can split up this problem into sort of 3 chunks and add that up. Yeah, kind of a lot to do by hand, though. Next one. Find the area of the region between the graphs of y equals x squared and y equals x cubed. So let's just look at the Mathematica picture here. Or maybe let's draw it first. So what we get, how about draw in red, y equals x squared. It's going to do something like this. And then maybe in green, y equals x cubed. Well, x cubed is going to go here. It's going to go there, and then it's going to sort of go up there. So what I'm going to get is sort of this intersection region in between. the Mathematica picture. So the sort of reddish one, probably hard to pick up, that's the x cubed. It ends up on top here, goes below, and then it goes negative. The x squared is sort of the parabola, this blue one. And there's my shaded region here. So what I need to do, first off, is find the intersection points. Find the point there where these are the same. Well, if x squared equals x cubed, you could divide both sides by x squared. You get 1 equals x. But when you do that, I'm dividing by x squared, so I have to worry about what if x equals 0. Well, that would actually be a solution, because I can't divide by x squared if x is 0. So I get one solution, x is 0, another solution, x is 1, so my intersection points are 0 and 1. Here, you might have been able to reason that, where 0 squared is 0 cubed is 0, 1 squared is 1, same thing as 1 cubed. So that means my area, I get an integral from 0 to 1. Top function, note, is actually the x squared. Bottom is the x cubed. So a lot of times students will mix that up thinking x cubed should be bigger, and that's true for x bigger than 1, but for x less than 1, actually x squared is bigger than x cubed. And now I do my antiderivatives. I get x cubed over 3 minus x to the 4th over 4 from 0 to 1. Plug in the 1s, I get 1/3 minus 1/4 minus 0 plus 0. And let's do this over 12ths. I get 4/12 minus 3/12. Answer here is 1/12. Kind of short and sweet here. If you'd managed to do the x cubed minus x squared, what you would have gotten was negative 1/12, and you should have been able to figure out that can't be correct because I need to have a positive answer because it's area. So you shouldn't just like change the sign to make it sort of the absolute value, but it'd be a clue that something went wrong, and often it's, you got a subtraction in the wrong area, or you lost a negative or made some little arithmetic mistake. Okay, here's another one. Find the area of the region bounded by y equals x squared, y equals 2 minus x, and y equals 0. So what we have, I'll just sketch this out and then show Mathematica. We have y equals x squared, some kind of parabola. Y equals 2 minus x is some line, and then y equals 0 is some line here. So now, this is, actually this 2 minus x goes there. There's a little bit of a question here. So let me show you the Mathematica picture here. So you have this line and this parabola. A lot of times people are going to be looking for this region bounded by the line and parabola, but then that's not really bounded by y equals 0. So I'll admit to saying this is a little bit ambiguous, but I'm kind of thinking of it as the triangular region here, or not triangular, but close to it. So it's really this region here. It's not a triangle because that parabola is curved here. But it's essentially a triangular region where I get one of the functions, well, each function is sort of one of the sides. Now, to be more precise, probably what we could have written here is to say that we want y less than equal to x squared. We want y less than equal to 2 minus x, and we want y greater than equal to 0. So that would actually determine that region precisely here. It's a little bit of ambiguity here. Some of this is just getting used to what's being said and what's meant. Hopefully, if you were doing this as an actual application problem, you'd be able to tell, oh, I want this red region because my x has to be positive with whatever I'm doing, and not this, say, let me highlight it as sort of this green region here. Oops, well, blue, but this green region here, and say maybe we don't want the green because that doesn't make sense in our problem, or go back and ask wherever you get the problem from, or look at it and figure out which one should it be. In any case, I'm going to do the red region. Now this introduces sort of a new wrinkle here. I have to find really 3 points of intersection here. So the first one I have, this is when y equals 0. Well, y equals x squared, that's at x equals 0. Y equals 0, y equals 2 minus x, so I get 0 equals 2 minus x. That's going to give me x equals 2. And then this third intersection, that x value, I'm going to have x squared equals 2 minus x. So it gives me x squared plus x minus 2 equals 0. So we get x plus 2 times x minus 1 equals 0. So I'll get x equals either negative 2 or 1. This is 1. The negative 2 is actually this intersection back there, but that doesn't really matter for the red region. Okay, so now when we do our area, what we're actually going to get 2 different double integrals. So when x goes from 0 to 1, not 2 different double integrals, 2 different integrals here, definite integrals. when x goes from 0 to 1, our top function is the x squared. Bottom function is 0. So I don't really need the minus 0 there, but I'll write it. When x goes from 1 to 2, top function is 2 minus x. And you could do a minus 0 as well. So this is really the new technique here, is we want to split this into two regions, because for some x's, one function is on top. For other x's, another function is sort of the top function. And when I do this, let's say integral of x squared is x cubed over 3, plus antiderivative, oh sorry, that should be from 0 to 1. Antiderivative of 2 is 2x. Antiderivative of x is x squared over 2. And that goes from 1 to 2. So I end up with, let's see, 1/3. 1 cubed over 3 is 1/3. 0 gives me 0. Plug in 2, that's plus 4. 4 squared, or 2 squared is 4 over 2. That's minus 2. Plug in the 1, I'll get another minus 2. And then I'll get a plus a half. So let's see, 4 minus 2 all cancel. So I get a third plus a half. So let's see, that's 2/6 plus 3/6. Answer here works out to be 5/6 here. And I believe, oh no, one more. I thought we might be done. That's 5/6. One more question. Not an area between two curves, though. So another one of these kind of annoying antiderivatives with the square roots here. And here we had another one of sort of manipulate this before. And I want to do a u-substitution. It's not clear what to make u here. What I'm going to do with this one is I'm going to pull that x to the 6th out of the square root. So it's going to be x cubed over x to the 4th plus 1. So I do 1/2 of the exponent. And now, hopefully what I can notice is x to the 4th plus 1 would make a decent candidate for u because it's under a square root. It's also in the denominator. Further, which makes me sort of really confident about this, is the derivative of x to the 4th is 4x cubed. So I get a 4x cubed dx. Okay. So now what I'm going to get, oh, before I do that, I have x cubed dx. So that's 1/4 du would be x cubed dx. So when I sort of switch to u, I get 1 over square root of u. So the square root of x to the 4th plus 1 is square root of u. X cubed dx is 1/4 du. Do your antiderivative. Well, let's just write it out. 1/4 u, this is to the negative 1/2 du. So that's 1/4. Add 1 to negative 1/2 gives me positive 1/2 over 1/2 plus c. See, so I do a 2 over 4 gives me a 1/2. U to the 1/2, that's square root of u, but u is x to the 4th plus 1 plus c. So there's my answer. And we might as well check this one because doing the derivative should be relatively simple here. So what I'm going to get, let's let this equal y. So just to check this, I can differentiate this function, see if I get square root of x squared over x to the 4th plus 1. So I get a 1/2 times 1/2 x to the 4th plus 1 to the negative 1/2. And then by the chain rule, I have to multiply by the derivative of x to the 4th, which is 4x cubed. 4 cancels with the 2's, and I get an x cubed over square root x to the 4th plus 1. Negative gives me an x to the 4th plus 1 to the 1/2. That's really a x to the 4th, well, square root of x to the 4th plus 1. And then I can rewrite this. X cubed is square root of x to the 6th. And then I can combine my square roots, x to the 6th over x to the 4th plus 1. That works out. Note we're making sort of the assumption that x is positive. If x wasn't positive, then square root of x squared would actually be negative x cubed. It really is absolute value of x cubed here, but I think that's a reasonable assumption to make, although based on the application, it may not be the correct way.